Hello and welcome to Doc Clay's Chemistry Lessons. Today we're going to be looking at the AQA AS Level Chemistry Practical Skills, Part 1. So by the end of this lesson you should be able to recall the 6 practical techniques for AQA AS Level Chemistry and have some idea of how you plan to use those in the exam. The first required practical activity then is to make up a volumetric solution and to carry out a simple acid-base titration. So both of these examples we've got highlighted below, and we'll start off by looking at the making of a volumetric standard solution. The first step then is to calculate how many moles are needed to make the required solution. In order to do that, we need to use our moles is equal to volume times concentration over 1,000, where our volume here is in centimetres cubed. Then you need to calculate the mass needed to make this number of moles from the previous calculation. And so you should remember that this is mass is equal to the molecular mass of the substance times by the number of moles. Now put a weighing bottle on a digital balance and weigh out the mass of the solid to give you an approximate mass of the solid. Tip the solid into a new beaker, weigh the weighing bottle again, and the difference in mass will give you a precise mass that you have weighed out. Now add distilled water and stir the solid until it's dissolved. Once it's dissolved, you're going to use a funnel to pour this solution into your 250 centimetre cubed volumetric flask. Now rinse the beaker and add those washings to the flask to ensure that any solute's been added to the volumetric flask. Then add distilled water until you reach near the top of the volumetric flask, and then finally add drop-wise the water until the water just about the bottom of the meniscus reaches the line. Finally then you're going to stopper the volumetric flask, shake it by inverting it upside down a few times, making sure it's mixed well, and then using the precise mass that you used earlier on, calculate the concentration of your new solution. And that's how you make a standard volumetric solution. Now let's move on to how we do the titration, a simple acid-base titration. And we can use our standard solution that we just made. The first step then is to pipette a known volume of the unknown concentration solution into a conical flask. You can tend to use about 25 cm cubed volume of this, but this does depend on the exact experiment you're doing. And using a larger volume can reduce your errors, and we'll see that in a future video tutorial. Then to the conical flask, add a few drops of a suitable indicator, and the suitable indicator is for a strong acid, strong base would be a phenolphthalein, which is pink in alkaline conditions and colourless in acidic conditions. You can also use methyl orange. Add the volumetric solution then to the burette, ideally using a funnel to avoid any spillages. And whether you use a volumetric solution in the burette and the unknown solution in the conical flask, or the other way round, doesn't really matter and depends on the practical that you're doing. Often the titration endpoint determines which way round you want those two solutions. Record then the start volume of the burette to 2 decimal places and record this in a suitable table. Then you're going to titrate the solution from the burette into the conical flask until the first permanent change in indicator colour appears, and that means lasting for approximately 10 seconds. Record the final reading to 2 decimal place and add this to your table. The first experiment is usually described as a rough, and then you're going to repeat the experiment until you get normally 2 or 3 concordant results. 3 to be on the safe side, and it's concordant when you're within 0.10 centimetres cubed of each result. This ensures that your results are reliable because the experiment can be reproduced or is repeatable. The final step then is to calculate an average of your concordant results, and then you can work out and do your amount of substance mole calculations for a titration. The second required activity then is the measurement of an enthalpy change, in which we use something called calorimetry, and we use the expression here that the energy change, or the energy in the reaction, is equal to the mass of the reactants times by the specific heat capacity of the substance being heated multiplied by the temperature change. And all the calorimetry ever does is measure the temperature change in an experiment, and there's 2 key ways that we will have seen doing that in our practical work. The first example here then can be done with a polystyrene beaker and a thermometer and a solution, and we can measure the enthalpy of neutralization. We can do this by adding known volumes of acid and alkali together, record the start and final temperature to come up with a temperature rise, and ensure that we stir the solution to ensure mixing. We can do the enthalpy of dissolution in a similar way, but this time you add the solid to the water and dissolve in the same setup, and again you record the temperature rise and stir the solution to ensure complete mixing. And in the same way we can do a displacement reaction where we add the metal to the salt solution, and in this instance we might have, let's say, magnesium to copper sulfate, and there you would measure the temperature change in the solution in the polystyrene cup again, each way giving us a way to measure the enthalpy of each of those reactions. The final way uses a slightly different calorimeter, which is called a bomb calorimeter, and that is for the enthalpy of combustion, and this will be where we have a fuel and we use that to heat a volume of water above it. So to do that, you weigh the fuel before the experiment, you burn the fuel to heat the water, measure the temperature change during the reaction, re-weigh the fuel afterwards, and then from that you can calculate the change in mass and hence calculate the moles of fuel used to burn and to measure the temperature change. There are then some problems with measuring the enthalpy of combustion, and they fall into 2 categories. The general issues are that you tend to get heat loss to the surroundings and heat loss to the container. Heat loss to surroundings can be minimised by improving insulation and adding a lid, and heat loss to the container by using things like polystyrene cups. While in combustion calorimetry, incomplete combustion can lead to reduction in the temperature change measured, and flammable liquids can also evaporate, altering the mass measurements that we take. Number 3 then in our list of required activities is the investigation of how the rate of reaction changes with temperature. How we do this then is down to the equation which stipulates the rate of reaction, and the rate of reaction is equal to the amount of reactant used or product formed in a given time. And what that means is we need a way to measure how much reactants are used or products are formed. Then to see how these change with temperature, what we're going to do is we're going to repeat all of our reactions at different temperatures, and to ensure that we get a stable temperature for all of our reactions, we're going to warm the solutions to a constant temperature using a water bath rather than just throwing those solutions together. The other thing to bear in mind in all of these repeat experiments is to keep the control variables the same between experiments to make this a fair test. And so the volume and concentration of solutions should be the same between experiments, and the mass and surface area of any solids used should be kept the same. Our first example then is in the formation of a precipitate, and this would be the reaction example of sodium thiosulfate, Na2S2O8, and hydrochloric acid, and they go to form sodium chloride, sulfur dioxide, and importantly sulfur, which is a solid precipitate which forms a yellow cloudy solution. To do this then, you put a conical flask on white paper with a cross, and then time how long for the cross to no longer be visible. Do this at different temperatures, as we said on the previous sheet, and ensure that you keep those control variables the same, in this case concentration and volume of mixtures. The next two examples then both look at when gas is produced. Our example first of all then looks here at the gas produced and is used on a mass balance. To do this then we mix the reactants together and measure a change in mass at regular time intervals. An example of this might be hydrochloric acid and calcium carbonate to make carbon dioxide. Remembering that in our repeat experiments we keep control variables the same, so if we've got a solid we might be keeping surface area and mass of calcium carbonate the same, and the volume and concentration of hydrochloric acid constant. Our final example then is when using a gas syringe rather than a mass balance, and here we would mix our reactants together again when we got gas produced and measure the volume of gas produced at regular time intervals. This might be an example here. Perhaps we might have magnesium strip reacting with hydrochloric acid, and again there to produce a hydrogen gas. Once again, if we're measuring this as a change in temperature, rate of reaction with change of temperature, we'd need to keep our surface area and mass of magnesium the same, and our concentration and volumes of hydrochloric acid the same. The fourth practical activity then is to be able to carry out simple test tube reactions to identify the following. So that is cations of group 2 and ammonium, and the anions of group 7, that's the halide ions, and also hydroxide, carbonate and sulfate. All I really want to do in this activity or this section is to identify some of the key words that we would use to describe observation in reactions. So the first example here is if we were to observe carbonate reacting with an acid as one of the tests, we would see bubbling occurring or effervescence due to carbon dioxide. The effervescence or bubbles is how we would describe the observation. If we can no longer see through the test tube when we mix two reactants together, then we describe the formation of a precipitate. So the halide ions with the silver ions will form coloured precipitate, white, cream and yellow, and some of those will redissolve when we add ammonia to them. I'm not going to go through each of those independently because they fall under really the category of those topics. But importantly for us in this section is the words that we use to describe our observations during these experiments. The fifth required activity then is a distillation of a product from a reaction, and this is done by setting up the apparatus with a round bottom flask attached to a thermometer, which importantly has a Liebig condenser which is horizontal rather than vertical. If it's vertical we have something called reflux, and then we gently heat the product and collect our product in a conical flask. So to start with, we start to boil the mixture and we heat it up. The chemicals start to evaporate, and then as they evaporate, they're hot, and then they'll reach our condenser, which is cool, and then as they cool, they recondense, and they will then be collected in the conical flask at the end, giving us a product which is comparatively impure, although purer than our starting product. After the first distillation then, there's usually some impurities, often water, along with your organic product, and these can be separated quite easily. So the separation, the first thing to do is transfer your first distillation to this device here, which is called a separating funnel here, and then leave it to settle into two layers. If it's a water layer, that water layer will appear on the bottom, and then that bottom aqueous layer can be drained off through the tap, leaving a pure or more pure top layer without any of the added water. To remove the final amounts of water then, we can add an anhydrous calcium chloride, CaCl2, which is a drying agent, leave for about 20 minutes, and that final product we can distill again, leaving us a pure organic product. The final required practical activity then is a test for alcohols, aldehydes, alkenes and carboxylic acids. We'll look at each of these in turns then. So the alcohols, the reaction is we add acidified potassium dichromate and gently warm, and if we observe the reaction, then the potassium dichromate turns from orange to green. If we do this with a primary alcohol, then a reaction is observed, and if we distill that reaction, so we have the Liebig condenser horizontally, we form an aldehyde, and we can test for the aldehyde. If we do it with a secondary alcohol, and we do it under reflux, this time the Liebig condenser is in the vertical position, then we will form a ketone. If we use a tertiary alcohol, there is no observable reaction. Just as a reminder then, here on the left hand side we have the Liebig condenser set up in the horizontal position, and we have a distillation, while on the right hand side here we have the Liebig condenser vertical above the round bottom flask, and there we have got reflux conditions. Test for aldehydes or ketones then, there's two ways of doing it. The Tollens reagent, which gives a silver mirror if an aldehyde is present. We add a couple of centimeters cubed of silver nitrate to a solution, add a few drops of sodium hydroxide until a light brown precipitate forms, add drops of dilute ammonia solution until brown, and then we add in our aldehyde or ketone and then wait for a silver mirror to form. The failing solution then, we observe a blue turning to a red solution if the aldehyde is present, and this is done by adding a few centimeters cubed of Fehling's or Benedict solution and then adding a few drops of the aldehyde or ketone to the test tube, leaving it in a hot water bath to warm for a few minutes. The test for alkenes then is we add bromine water and it turns from orange to colourless if the alkene is present, and if we know exactly how much bromine we add, we can determine how much alkene is present by working out the mole ratio of bromine to the alkene. Finally then, the test for carboxylic acid. Effervescence or bubbles are observed on the addition of carbonate. It's also possible to test for a carboxylic acid using pH paper, so universal indicator paper, and it should be acidic, we should see it red, or perhaps even a pH meter to read a acidity of something which is less than pH 7. So just to recap, at the end of this lesson you should be able to recall the 6 key practical activities for the AQA AS chemistry course and have some idea of how you might be expected to use those in the exam. Thanks for watching, and I hope to see you soon. Bye for now.